Hello, everyone. Welcome to our webcast on sensors, power, and the Internet of Things, how big data is influencing how we design, and technologies that enable a wider use of sense data. I'm Nick Davis, your host for today's webcast. I'd like to welcome our presenter, Greg Rice, who is an OnSemiFinalMP4 Business Unit Technical Marketing and Applications Manager. Greg has more than 20 years of experience within the semiconductor industry, with a focus on high-speed analog and RF products. Greg has held positions in design, product engineering, applications engineering, and now technical marketing management. At OnSemiFinalMP4, Greg is currently working to bring to market a new smart passive sensor technology that has a potential to revolutionize the sensor industry. Greg, welcome.
Thank you.
Before I turn it over to you, Greg, I'd like to remind everyone to submit their questions via the Q&A widget. We'll answer as many questions as possible at the end of the presentation, and we'll reply via email to the questions that we do not cover. So let's get started. Greg, over to you.
Okay, thank you. Welcome, everybody. I'll go ahead and get started. So the evolution of the Internet of Things is an exciting opportunity for all of us as engineers, system architects, device end users, and product developers. Today, I'll review sensors, powers, and the Internet of Things, including a review of a new battery-free wireless sensor technology that will enable growth in Internet of Things applications. To give an overview, I'll start off with some discussion of what we mean when we talk about the IoT, since the definition of the Internet of Things can be different depending on who you talk to. I will give my view on what we mean when we say IoT, as well as review some estimates on the overall size and growth projections for the IoT over the next 5 years. This will lead into some details on a new sensor technology that complements traditional electronic sensors and how this wireless sensor architecture can be used to provide connectivity to the IoT. Finally, I'll review some practical applications being developed using this new wireless sensor technology. So what do we mean by the Internet of Things? IoT has become one of the common buzz phrases associated with new technology. A lot of people talk about Internet of Things. We have trade shows and conferences dedicated to IoT, but it seems like the specific definition of the Internet of Things is somewhat in flux. I found if I go around at a conference or trade show, if I talk to 5 different people and ask them for their view on how they define IoT, it's not uncommon for me to get 5 different responses on what IoT means to them. I think this is natural. It doesn't have necessarily a set definition, and I think depending on how people use the Internet of Things, they may have a different view on it and how they define it. For me, as a component developer, when I think of the Internet of Things at a basic level, I think of electronic devices that are able to communicate to each other through a common interface. Oftentimes, wireless communication is used with the data being passed from one device to another through a cloud interface. I believe that IoT really began to grow when the first smartphones were introduced about 10 years ago. For me, this was my first experience with a device other than a computer that was able to connect to another device and send data back and forth. From there, many different devices have become smart. We have smart thermostats in the house, which enables homeowners to monitor and control the temperature of their home from hundreds or thousands of miles away. There's smart coffee makers that can monitor coffee level, automatically order coffee refills when needed. Automobiles are becoming connected to make transportation safer and more efficient. We have industrial applications that can now send data to the cloud for evaluation and monitoring. Ultimately, the IoT is a network of various types of devices communicating with each other, sending data to each other back and forth through the cloud. The data sent typically is going to be generated through some sort of sensor. A sensor is something that's used to determine the temperature of the device, position, pressure, moisture level, etc. And it is the core to generating that data. As the IoT continues to expand, the need for additional sensors and sensing technologies is a requirement to enable this growth. So this slide, I love the outdoors. I live in a suburb of Phoenix, Arizona, and I'm surrounded by lots of open desert, which gives me some great views of the night sky. I have 2 young kids, and they love to go outside and look up at the stars at night. When I go out with them, I'm continually amazed as I gaze at the vastness of the night sky. For thousands of years, civilizations have looked at the same stars and the vastness of space. Over time, our understanding of the universe changed. In 1543, Copernicus demonstrated that the Earth revolved around the sun. In 1609, Kepler told the world the planets moved in elliptical orbits and not perfect circles. Galileo looked further and discovered 4 moons orbiting Jupiter in 1610. Last century, Hubble discovered other galaxies, and after a space telescope named after him transmitted pictures back, we're finally realizing just how big space is and how little we know. Even though since the beginning of time we've looked at the same sky, our understanding of it continues to expand. In some ways, this is how I think of the IoT and how it's evolving. Every year we get new products, new opportunities, new technologies, and new ideas which expand our understanding, and our world is becoming more and more connected. So with that, like say the IoT is like the sky. The Internet of Things is big, it's boundaryless, and it is continually getting bigger. So how big is the IoT? It depends on who you talk to, the models for the rate of adoption, and how quickly we can build and scale the IoT ecosystem. Gartner says there will be 26 billion connected devices by 2020. Cisco says that there will be 50 billion. Intel says there'll be 200 billion, and the IDC says there'll be 212 billion. In any case, these are all really big numbers, well into the billions. These numbers represent incredible growth in the industry. Today, there's somewhere around 15.4 billion connected devices, and according to IHS, that number is expected to expand to 30.7 billion in 2020 and 75.4 billion in 2025. So the real question for us to continually assess and evaluate is how big is the IoT going to be in 10, 20, 30 years from now? If we think about the potential, there's this great quote from Cisco that says, only 0.06% of things that could be connected to the Internet currently are, which means 10 billion things out of the 1.5 trillion that exist globally are currently connected. So however you look at it, it's a huge opportunity over the next few years. So let's look at the IoT tomorrow, what it looks like and what we need to do to ensure scalability and success. Historically, the market fueling the connected devices has been the wireless and communication market. Mobile phones, tablets, and computers have historically been the foundation for growth, with growth in smartphones expected to double over the next 3 years. The IoT coming online is changing the types of connected devices with some very exciting technologies moving forward. Connected home. Connected cars are going to double as autonomous driving and other features come online. Connected home is another area with the number of connected devices within the home expected to go from about 9 devices per home now to around 500. Another area with tremendous growth is within the smart city and infrastructure arena. As populations grow and cities optimize living experiences like lighting, parking, communication, and energy management. There's a tremendous opportunity for new technology products and applications. So overall, over the next 7 to 8 years, the number of connected devices is expected to increase by almost 5 times. And all of these connected devices push an enormous amount of data to the cloud. The global daily traffic is expected to go from roughly 2 exabytes today, increasing 60 times to 120 exabytes in 2020. So with 120 exabytes of data, one of the major growth drivers for IoT is big data. as applications and products come online, there's a wide variety of data, and the data will have different use models and needs. Think about the challenge of storing, processing, and analyzing data from mobile health devices, agricultural, industrial automation, and our homes. Chris Murphy, editor from Information Week, says, one of the myths about the Internet of Things is that companies have all the data they need, but the real challenge is making sense of it. In reality, the cost of collecting some kinds of data is still too high, the quality of the data isn't always good enough, and it remains difficult to integrate multiple data sources. As solution providers and technology developers, one of our primary challenges is to provide the correct data, which means accurate data and the right amount of data, which can seamlessly integrate into the IoT ecosystem. So as an engineer, one of the exciting thing, one thing I like to do is being able to participate in key developments and the rollout of technology. So I'm sure we've all seen evolution of the smartphone. Previously, we looked at the phone as a single-use fixture secured to the wall, just something to voice communication back and forth. Motorola developed the first cellular phone, and untethered the phone and made it mobile, but for all intents and purposes, it was still just a phone. Nowadays, our smartphones are computers, video cameras, calculators, music players, game consoles, and much, much more. We see the same trend in other markets also. Look at watches. For centuries, people told time by following the sun. And then came the digital watch, and now Garmin has this new Phoenix watch, which is really a true story of integration in data. The Phoenix watch not only tells time, but it records workout data, continually monitors heart rate, calculates VO2 max, monitors sleep patterns, receives messages, and so on and so on. We continually see this pattern of innovation and integration starting in consumer and computing markets and then moving to other markets. We see this trend in lighting, home automation, automotive, smart energy, solar, and critical infrastructure. Again, as technology developers, we have 50 billion devices to connect over the next 10 years. So now that I've gone over some of the high-level aspects of the IoT, kind of the sizing and the growth projections, I'd like to shift the focus down to some of the lower levels, particularly looking at how sensors fit into the architecture of a typical IoT network. This slide shows a typical network for Internet of Things. At the edge of the network, shown on the left side of this slide, we have the sensors which generate the data. A sensor is just something that takes a physical parameter such as temperature or moisture, and it will convert it to an electrical signal or data. Once the sensor has generated this data, it will be passed to some sort of device, a platform hub that does some aggregation, takes the data from multiple sensors, and can do some basic formatting and analysis of this data. From there, the platform hub or gateway provides the network connectivity to send the data to other devices for additional analysis, logging, etc., which completes the IoT connection. This type of network arrangement is common across multiple industries, including transportation, home automation, supply chain, medical, industrial, and even livestock and agriculture. So taking a closer look at the sensor part of the ecosystem, this is a typical architecture for an electronic sensor. In general, you'll have three key blocks that make up an electronic sensor. You have, of course, the sensing element. That is the part of the sensor that reacts to the physical environment. So if it's a temperature sensor, the sensing element will have in physical change to change the electrical parameters of it based on temperature. If it's a moisture sensor, it will change based on moisture, etc. But you have the sensing element. And then in addition to that, you have what I call sort of these support blocks. You have power. Obviously, you have electronics on there. So somehow you need to power the sensor. Typically right now with electronic sensors, the power is either going to be wired power or some sort of a battery if it's a mobile sensor. And then another block you have on there is this data processing and connectivity. The data processing and connectivity is generally going to be a microcontroller, could have some logic, clock circuits, etc. But that's what actually gets the data out of the sensor. This works fine. There are some challenges with this type of architecture. What happens is, since you have all of these blocks for every sensor, your cost to scale is directly proportional to the number of sensors. And what we found is that for some applications, using a traditional electronic sensor becomes prohibitive due to cost or also form factor-wise, because with all of these components necessary in the sensor, you can only make the sensor so small. So as a complement to that, we've been developing a new sensor technology that decouples the sensing element from the power and control. So that's what we've referred to as these smart passive sensors. So it's a battery-free, microcontroller-free wireless sensor. How it works is it basically has an IC, which the center of this slide shows a typical sensor. There's an IC, single chip, mounted to a wireless antenna. So that's what we're calling the smart part of it, does the sensing. We say passive because it works from energy harvesting. The smart passive sensor is part of a system, so there's a counterpart to that that has a shared essentially power and computing block. So the sensors themselves are powered through energy harvesting, and then the sensing. So this slide gives a little bit more detail on how these smart passive sensors are architected and how they work. Talk about the function block. So on the kind of top left side of this slide, you see another view of the sensor. Again, what we're calling the antenna block. So on that is a printed antenna that's tuned to get the RF energy. And then on that also there's a sense element which will be designed depending on the type of parameter we're trying to sense. And then you have a single chip IC built on that. The other part of the sensing system is what we're calling this power, microcontrolling, and processing block. So that's on the right side. Effectively, we also call it a reader. So what it is, it's a reader or interrogator that can talk to multiple sensors at one time and collect the data. So the reader sends out RF energy through an antenna, wirelessly goes to the sensor does energy harvesting, powers up the sensor, and then does communication back to the reader. And the reader can do some data aggregation, etc., and that's how the sensors function. So currently, this technology, we're using it to sense temperature, proximity, moisture, and pressure. So with this type of technology, and again, I want to highlight again, this is not looked at as something that will replace traditional electronic sensors. What it is effectively a complement. It will open up applications that were really not possible or feasible to do with traditional sensors. Again, we have some unique features. They're battery-free and wireless. So that means you can put them in locations that are hard to access. They can be underground. They can be placed within a wall. They can be placed in an area where you don't want to have to access for maintenance, etc. And again, they're designed. They can be very thin. So again, you can put them in areas where you don't have a lot of space to physically locate something. And then also they are, because we're separating the sense element from the power and control, the cost to scale. So if there's an application where there are many sense nodes required, the cost to scale with this type of approach is much less than using a traditional sensor. So I spent a couple of slides talking about the details on the sensor. Now I'm going to move on a little bit to talk about the other part of the sensor system, which is really the reader or the sensor hub. That is what provides the RF power and the connectivity. So this is looking at it, as you can see here, this diagram, we're showing the sensors kind of on the far left side. These are the wireless sensors, and they communicate wirelessly to what we call the sensor hub or reader. The sensor hub integrates two key blocks. There is the reader, what we're calling the reader module, and that is effectively a dedicated RF transceiver module, which does the RF communication. It will have dedicated firmware drivers, etc. That gets the raw sensor data out from the sensors. From there, the reader module is going to be connected to what we're calling a processing module. The processing module does data aggregation, some basic formatting of the sensor data for additional analysis, etc. And then also the processing module will provide the connectivity. Generally, the connectivity could be Wi-Fi, Ethernet, Bluetooth, etc. Generally, with the processing module, you have the ability to kind of include any kind of connectivity that is desired. So with this type of approach, this is another view of kind of how the sensor IoT architecture looks when using the smart passive sensors as part of the system. So again, on the bottom left here, we show the sensor hub, which does the RF communication. It will have some application software on it and some connectivity that's talking to the sensors. From there, the sensor hub sends the data to the cloud in this example, and then also connected to the cloud could be various other connected devices to complete this whole IoT connectivity and functionality. So that was a somewhat quick overview of the smart passive sensor system and the components. With that, I will move into some practical applications. As I said, these sensors, they don't fit everywhere. They're not necessarily a replacement for the traditional sensors, but for some applications, they have a very good fit on the technical side. So I'm going to go through and just talk about some of the applications where this technology is being used. So one application is in the industrial segment, and this is in power switchgear for preventative maintenance. So these are big, large boxes of switchgear where there are lots of bus bars and cables connected together to route power. So we could be talking about thousands of volts or thousands of amps being routed. These would be running, factories or facilities. Any kind of large buildings will have this switchgear. So the issue historically is if these connections become degraded, if they get corroded, or if they're bolted together and if they're not torqued quite correctly, that results in a high resistance connection. And if any electrical engineers over there will know, as you run more current through a higher resistance, you burn more power, which translates to heat. So facilities engineers really want to understand what the temperatures are of their bus bars. The challenge is right now this is a manual process to monitor that temperature because they don't want to run any wires on bus bars that are already running at a high voltage, high current. They don't want to have any fear of or possibility of arcing or shorting out or anything like that. So right now it's a manual process. Facilities engineers will go into the factory, open up the panels of the switchgear, and they generally will use an infrared camera, and they'll scan and they'll look for any hot spots. That's commonly on an annual maintenance cycle. So when they do that, they get one data point in a year. So if they see something that's a little bit warm, they really don't have any trend data to know if that's something that is operating at a normal temperature or if it's at a expected temperature due to a higher load or if it's something that is an issue. So there's really a desire to have an ongoing continual temperature monitor with this. One of the benefits of having continual data is you can send it to the cloud, you can do trend analysis, you can see what's going on. This is just an example, kind of a theoretical plot showing temperature over time. This would be, say, of 3 phases of power in some switchgear. You can see, starting at the left over time, it seems like all 3 phases are running at some nominal kind of temperature level. At some point, all three phases of power have an increase in temperature. That could be attributed to an increased load on the switchgear, so that could be within normal parameters, so nothing to be concerned about. And then at some point, you see two of the phases start to drift back down to a normal nominal temperature, but the third phase, this yellow phase, starts to go up. So if you have the continual data on this and you can see the trending, you can raise the flag on that and do some inspection or maintenance of that before there's a catastrophic failure. So this is a closer look of how this system has actually been installed in some switchgear for a case study. One thing that I want to point out here is in the center of the slide, that black square, that's actually the sensor, so that's a slightly different form factor than what I showed previously. The reason for that is because this is being placed on metal surfaces, and we also needed to make it a smaller form factor, so we used a different design, but the technology is the same. So these sensors were placed on circuit breaker contacts and on cable connections to bus bars. We also installed multiple reader antennas to get coverage and read all the sensors, and dedicated readers. Since this is in industrial facilities kind of environment, the readers connect to the existing SCADA system used as a control system in the facilities, and it sends the data over a Modbus protocol using either an Ethernet or an RS-485 hardware connection. So healthcare, this is another area where the smart passive sensor technology is being used and offers some benefits. Currently in a hospital, the nurse workloads are continually increasing, which makes it more and more challenging for caregivers to really make it be effective in monitoring the patient's status. They can't be in every room all the time. What happens is there's some risk of if a patient is out of the bed, it could be normal, the patient is just out of the bed walking or moving to a chair, or if a patient could have fallen out of the bed and needed some assistance. We're using our smart passive sensors integrated into the bed to detect the moisture in the human body to detect if someone's in the bed or not continually. You can also do relative temperature monitoring of the patient. It's not a medical grade temperature, but you can do trending, and if you see if a patient temperature spikes up several degrees, that could raise a flag for the nursing staff to go and get a medical grade temperature reading to see if there's something going on. You can also tell if the patient is restless in their bed. If you place multiple sensors in the mattress, you can tell if the patient is moving around, indicating they're restless. If they're restless, that could be an indication that they're in pain. Perhaps they need some medication, or also it could be an indication to the nursing staff if they need to do a procedure on the patient and they're overly restless, that might not be the best time to do that procedure, so they can take that into account. Also, with the wireless sensor monitoring, you can monitor fluid levels. So you can look at IV bags. If they're getting low, you can raise a flag on that. Catheter bags, you can tell if they are getting filled up or not. Also, you can detect if the bed linens need attention. So we're working with partners to do a full development to kind of make a connected, smart hospital bed. So this is another view of it. As I mentioned, in the mattress of the bed, we integrate multiple sensors to detect the moisture in the body to indicate the bed presence or exit. The reader solution is integrated into the bed frame. So effectively the electronics for the reader hub are built into the bed. It has existing electronics in it. And the reader antennas will be integrated and installed in the footboard and side panels of the bed, making it a truly seamless integration, giving a lot more data continually on what's going on with the patient. So this will improve the patient experience and then also make the hospitals and caregivers be able to give better care more efficiently. So another application is in data centers, looking at server racks. As data centers are growing, they're becoming larger and larger. There's more equipment is being installed in these data centers, and the cost of monitoring the condition of that equipment is going up and up. we've talked to people that want to understand what the temperature is at the air inlet of each server within a rack, so they can effectively monitor and optimize the heating and cooling of the data center rooms on a per rack basis if desired. Right now, servers can tell you the temperature of their processors, but if you get a server that has a processor that's hot, you don't know why. It could be a processor could be hot because the air inlet temperature is too high. It could be hot because the intake fan is not working. It could be hot because there's too much load on that processor. You really can't tell if this processor is hot. So with having more data using our smart passive sensors, you can do some correlation to air inlet temperature, outlet temperatures, et cetera, to try and get a real complete heat map of the whole system to see what's going on. And also, again, look for trending, et cetera. So we're doing a full development on this. We're using on-metal temperature sensors placed on a per server. And again, we're integrating the readers and antennas within the server racks. One thing that I did not mention previously is that these sensors are built using the existing RFID technology. As part of that, you get asset tracking. So with that, you can tell if you have a server, the IT manager can tell not only that a server is on the network, but they can also tell specifically where that is physically located. I've talked to several IT people, and they all tell me that they spend a lot of time physically trying to identify where a piece of equipment is located, because sometimes things will be moved from one rack to another rack to make space, and it doesn't always get documented. So just because they can see that something is electrically on the network, they really don't know physically where it's at without being able to go out and look for it. With our sensors on the servers, they'll know at least down to the rack where each piece of equipment is located. So this is a closer view. This is actually a rack of a bunch of hard drives. So effectively, we put 40 sensors on this rack of drives. It was a 42U high standard rack. And then we integrated the reader and antennas into the rack. You can kind of see on this close-up of the photo in the center, that small black square or rectangle with the white writing on it, that's our sensor. So here's another view showing an empty rack and how the sensor hub or reader is integrated into the rack. Effectively, the hub is made as a relatively small form factor, so it can be installed either in the sides of the rack or on the top or the bottom. And then the reader antennas are designed with a small form factor. They're a magnetic mount, and they mount to the rack doors or rack sides with the appropriate cabling. So another application where we're using the sensors, I just have this one and one more, we're calling digital farming. So this is in the agricultural and livestock areas. So right now there's a movement for beef and basically cows and pigs for all the feed animals. There's a movement to have less medication on the animals if they're not sick. So historically, the farms at a feedlot will, when they get a lot of cattle in, as part of the intake, they all get antibiotics administered to them, whether they're sick or not. So there's a movement both from the federal administrations and also just from consumer demand. People don't want antibiotics and et cetera in their meat, in their animals. So because of that, they're doing less of that, so that's going to lead to probably an increase of illness in animals. So with that, there's a desire to be able to have a way to indicate when an animal is sick before it becomes a critical issue. So the solution to that is to take our sensor, make it in an implantable or an injectable form factor, and put these in the animals. That way you can get continuous reading and know you can detect a spike in temperature or fever before the animal shows visible signs. Right now, this is a manual process. The farmer will essentially keep an eye on their animals, but they typically won't see if an animal is sick until they're showing many visual symptoms, and sometimes by that time it's too late to save the animal, so that results in the loss of the animal and then additional cost to the farmer. So this is a solution. We are working with some partners to implement it effectively on cows. We're looking at doing the injectable kind of in the ear to get the ear sensor, and then in a similar application in pigs. So we have some initial prototypes. This is what they look like. It's essentially a long glass tube that has our technology inside on a small substrate. The tube is a 5 millimeter diameter. So you can see it on the bottom left here. You can see the picture of it for size. You can see relative comparison to that next to a quarter. We have initial prototypes. We are working with some customers to get some additional feedback, and we'll continue to refine this solution based on customer feedback and how the technology responds. So the last area that I'm going to talk about for practical application for this technology is in the kind of cold chain and logistics field. So this is when they're shipping goods, pharmaceuticals, produce, etc., worldwide. So there's a lot of cost associated with goods that are lost due to excursions in the temperature during shipment. It could be, pharmaceuticals are not stored at the right temperature, so they're no good to use. It could be a shipment of produce gets spoiled because it's at too high of a temperature, etc. Right now, the end store or receiver of that pallet of goods don't necessarily know if something is good or not when they get the truck, and then they can get something and start unloading it and realize that everything is spoiled. And at that point, they don't have a lot of tracking to understand, did it spoil during shipment? Did it spoil because it sat on the receiving dock of the customer for too long, etc. So the solution to that is to use our smart passive sensors to continually monitor the temperature and provide alerts. If something happens with a truck, if the temperature is getting too hot, it can send an alert out to either divert the truck to somewhere to unload that cargo or just change the temperature of the cargo bay of the truck. So this is a low-cost solution because, our sensors are very low cost compared to other alternatives. So, and it does give unique tracking because of the RFID aspect of it. You have a unique ID for each package that has our sensor on it. So another view of this, what we're calling the cold chain. So these are effectively large trucks or containers that get shipped by rail. The temperature sensors can be attached to cartons and read by readers and antennas that are placed inside the trailers or the containers. We're looking at possibly developing some battery-assisted temperature sensors inside the carton to be read by the receiving warehouse existing RFID infrastructure. And then also the battery-assisted temperature sensors can be integrated into the shipping labels of individual cartons to be read by receiving warehouse RFID infrastructure. So that's another exciting thing that we're looking at, and we're continually finding new applications for this technology. It's really fun to work with. So in summary, just like to kind of recap what I talked about, the Internet of Things is big. There are billions of connected devices generating exabytes of data, and regardless of the absolute numbers, it has a tremendous growth rate projected for it. Sensors are used to collect the data for the IoT out at the edge. I talked about our battery-free wireless sensors, which will complement traditional electronic sensors and enable end users to collect data in areas not possible with traditional sensors. I talked about the sensor hub or reader, which is a key component to aggregate sensor data and provide the IoT connectivity. And then I reviewed some of the applications we're currently developing for these wireless sensors. So with that, I would like to say thank you, and we can go ahead and open it up for questions.
Hey, Greg. Thanks a lot for that presentation and sharing your knowledge. I think it was fantastic. So it looks like we've received a number of questions from our audience, and we'll go ahead and see if we can get through all of them now. So the first one is, how close does a sensor need to be located relative to the reader?
Okay. Yeah, so that's a good question. So as I mentioned, this is a It's a system, so we don't, we're decoupling the power and computing block from the sensing, but the sensing does need to, be close to the reader. So the answer to that is effectively there's a reader and a reader antenna, and it does depend, but generally we get a range of the sensor to the reader of on the roughly into 3 to 5 meters.
Okay, thank you. Question number 2, how many of these sensors can be read by a single reader?
Okay. Yeah, so that is one thing, since these sensors, I think I mentioned they're built using existing RFID technology. The difference is with the sensors, with RFID you just get an identification for asset tracking. With the sensors you get all the RFID information plus the environmental conditions, so you can get temperature, moisture, etc. But back to the RFID, one of the benefits of using that is that RFID was designed to talk to hundreds or thousands of tags at a time. So with that, yeah, one reader can access hundreds of sensors simultaneously.
Okay, next question is looks like kind of a two-part question. From what I understand, the readers provide the power to the sensors. So at what frequency band do they use, and what RF field strength in units of volts per meter is needed to make them work?
Okay. So let's see. So let me see if I captured all of it, not. But so I think one part of it was the frequency band. So yeah, so it's built on an RFID standard. It's a UHF standard, and the frequencies it operates at depends on the region. In the FCC or North American Asia market, it's a 902 to 928 megahertz. And then in the European markets, it's an 865 to 868 megahertz. And then what was the second part of that question again?
The field strength in units of volts per meter.
Oh, okay. So it's I'd have to do I don't have the conversion in front of me for volts per meter, but it's at the reader antenna. There's a 30 dBm output power, which is regulated by the standards bodies. Okay,
great, fair enough. So the next question, how long does it take to read data from a sensor?
Okay, yeah, we do have, so some applications, the speed to read the data from the sensor is really not that critical. A lot of these that I mentioned, kind of the bus bar temperature monitoring and that kind of thing, we're expecting temperature changes in minutes or hours. A single sensor read is roughly 100 milliseconds, but that does depend on several factors. But in general, yeah, we figure 100 to 200 milliseconds per read.
Okay, and it looks like that's all of the questions right now. We can go ahead and wrap up, or if you want to just hang out here for a couple minutes, Greg, and see if more come in, that's fine too. So I'll leave it in your court.
Okay. Yeah, sure. I did put my email address is shown there. So if anybody does have any follow-up questions or would like to reach out to me, feel free to contact me.
Okay. A new question came in. So any applications with strain gauges for IoT?
Okay, that's a good question. So not so far. We do have a variation of the control IC coming out that would potentially work with a strain gauge, but so far we have not been actively developing that or developing that application. But that is on our radar because we have had some inquiries for seeing if we can interoperate or do kind of a pressure application using a strain gauge.
Okay, great, thank you. So another question came in here. Can you give ways or examples of going batteryless or energy harvesting? So examples of one versus the other.
Okay, So I think, so in general, at least for the technology I'm talking about, we kind of use, when I talk about battery-less or energy harvesting for at least these sensors, it's kind of one and the same, but how it works, and I'm not sure if I'm exactly addressing the question, but yeah, so how it works is the reader, it sends out RF energy at a certain power level, and the IC, the antenna on the sensor is designed to efficiently receive that RF energy and get that into the chip. The chip is designed to work at very low power, and it does have circuitry on there that can take that RF and basically convert that to power to run the IC circuits.
Okay, that makes sense to me. Hopefully it makes sense to the person asking the question, so thank you for that.
Okay.
So how about we give it a few more seconds here for maybe some more to come in, and if not, we can wrap it up. Okay, a question came in. Are there any development kits available?
We do have, yes, there are. We have essentially, a basic, we have developer kits for specific targeted applications, and we also have kind of a general purpose kit available. So I think the best thing would be either contact me, or you can go to our website and you can find information on it there on how to get it. But the answer is yes.
Okay, perfect. Okay, another question. Looks like maybe a follow-up to the previous one. And are there APIs to connect with other small form factor IoT boards?
I guess I mean, I think at a high level, I would say yes. I would need to, I guess, get a little bit more understanding of specifically what you're looking to do. But I think the idea is with that sensor hub, basically you get that sensor hub, it will have its own API talking to the reader module, et cetera, to get the data out of the sensors. And then from there, once you have the data into the sensor hub, then it's really just, I think it's just a matter of, providing whatever connectivity is needed to pass the data from one device to the next.
Okay, I have a question here. Maybe in general terms, not specific to the presentation here today, but the question is, do you have career advice for young aspirants who want to make career in IoT?
Oh, that's a good question. I mean, I would think, just my opinion, I think now is a good time to be getting involved with IoT because of, we went through it earlier. I think it's really just starting to snowball and really grow. For a new engineer, I guess I would advise, just to stay involved. That's good to have some understanding of hardware and software, and to be able to work in the lab and experiment with systems and get things working. Because a lot of IoT is really driven by new, unique applications that we weren't really even able to do a few years ago.
Okay, it looks like that's all the questions. So again, thank you, Greg, for presenting this information to us and for sharing your knowledge. And I want to thank the audience as well for calling in and participating. So thank you again, and have a great day.
All right, thanks, everyone.